Hello, I'm going to talk about floating and sinking today. So floating and sinking, and that obviously use a ruler, unlike me, that was a very bad example. And this will relate back to last lesson's work as well on density. So you might want to have another look over those two videos first before you watch this. There's only a few overlaps, but it might help. So first of all, I wonder if maybe in primary school you saw something that looked something kind of like this. I can't even remember what it looked like on the top. What did it look like on the top? I don't know, like some kind of handle probably. And they were usually quite colourful, like bright red, bright yellow, bright green, bright blue, and they had numbers on it. And you might have used it to hang something on the end, or you might have used it to, hooked it onto something and pulled it along. And then inside there was a spring, and we call this a Newton meter. And we use those on, I actually put Newtometer. Whoops. My bad. Newton meter. And we use that to, unsurprisingly, measure the force of different objects. Okay, hence the Newton, because remember, forces are measured in newtons. Now, if I hang something on the end of this, let's say a block. I'll talk about a block quite a lot in today's lesson. Here's my block, and it might say on my Newton meter, if I hold up this Newton meter and let the block hang on the end, it might say that the force of the block is, just going to make this up, let's say 5 newtons. Okay, now what is that 5 newtons for? That's the weight acting on the block, capital W, remember, pulling down on the block, so that would be 5 newtons. Now, imagine if I've done that and then I decide to put the block into some water. So imagine I've got a big bathtub again. There we go. Just like the one Archimedes got into. It's filled with water. Here's my block. There we go. Here's my Newton meter, which is for some reason quite big relative to the bath. So a reminder that drawings are not to scale. Is it still going to say that my block is 5 newtons? If it was going to say 5 newtons, I wouldn't have wasted my time drawing this bathtub out. Okay, so what's actually going to happen is it's not going to say 5 newtons anymore. It's going to go down. So let's just say it's now 3 newtons. Why would that happen? What's happened to that block between being in the air and being in the bathtub? Nothing's really changed about the block. We haven't made it smaller. We haven't changed the mass of the block. So why would it suddenly be less in the water than it was out of the water? Well, this 5 newtons is the resultant force on that block. So that overall force, one force acting on this block, in this case it's the weight. Now when you're in the bathtub, you've still got that weight, which was 5 newtons. Now the only reason it could possibly be reading 3 newtons on this is there is also an upward force, which must be, hopefully you can work it out before I write it down, 2 newtons. So the overall force, if you remember how to calculate your resultant forces, we've got 2 newtons upwards. Should have drawn that was very bad. Should have drawn a bigger arrow down there. This is my 5 newtons. Well, 2 up, 5 down, that leaves me with 3 newtons downwards. Okay, so that's why in water things appear to have less weight than they do, even though that's not actually the case. So you might find that if you've ever been in the swimming pool or in the ocean, it's actually easier to pick things up, because there's also up thrust helping you to pick that thing up. I know a lot of my students have said that they've picked up their brother or sister in the ocean and it seems a lot easier, but when they've tried it out of the water, it's not quite so easy. And this is the reason why. Now, what is the name of that force pushing up on it? It is called up thrust. And that's really what this lesson is about. So up thrust. Now, that is the force that pushes up on objects within liquids. And the first thing I want to tell you about it is, well, firstly, remember it's a force, so it's still measured in newtons, as you can see up here, 2 newtons, but also that to calculate the upthrust, or to work out what the upthrust is, or what it's equivalent to, it's equivalent to the weight of water displaced. And I'll just expand on that now. So if you watched last lesson on density, we talked about the amount of water displaced is how much water an object's had to move out of its way so that it can, rest there in the water, or, be within that water. So I'm going to do another block example. This is my water. Here I've got a block within water, and my block's had to move this amount of water, I'm not going to colour in the whole thing, out of the way to make room for the block. So there is this amount of displaced water. So in last lesson, when I had that mug and I dropped, what did I put in there? I put another little glass inside the mug and it pushed water out of the mug. I don't know if you remember. I put something in there and it made water spill out of the edge, but I had the water in a tray, the mug in a tray, so some of the water went into the tray, and then I said we can find the volume of that by putting it in a measuring cylinder, or although I didn't think of it at the time, I could have just put it in a measuring jug to show you, to tell me the volume of that water. So if I got this water here, let's imagine it's the water displaced by the block this time rather than me putting something in a mug, then if I could weigh that, if I could find the mass of that, put it on some scales, then let's say I put it on some scales and it said it came to 4 newtons, just made that up. Obviously, if you put it on scales, most scales will tell you something in kilograms, not newtons, but you can get ones that give you the weight rather than the mass. So 4 newtons is the amount of displaced water. So what's my upward force acting on that block? It's 4 newtons. Okay, so the upthrust equals the weight of the displaced water. So again, this time if I put a ball in the water, this amount of water I've had to move out of the way to make way for the ball. If I measure the weight of that, it tells me 2 newtons, then I know the upthrust, so the force pushing up on the ball, will be 2 newtons. Now obviously it doesn't have to be water, it could be something else as well, but we will talk about water in this case because that's the common scenario. So I'll need to come back to that. Let me just move the paper up a bit so you can see a bit more. I want to talk about some scenarios then. Make sure you see that. It's a bit annoying, isn't it? So, scenarios. Number 1. Let's say, remember, what did I say the symbol for weight would be? Capital W. So I'm going to put capital W rather than writing out weight each time. Weight of the block. Let's say that is bigger than or greater than the weight of the displaced water. So imagine I weigh this whole block and it says 7 newtons, whereas the weight of the water it actually moved out of the way was only 4 newtons. Okay, that's what this scenario is describing. What will happen? Well, the block will sink. That's not surprising. That's basically saying, you know, the weight of the displaced water of this block is 4 newtons. Again, I should have drawn that longer. Remember, the size of the arrow is important when you're drawing force diagrams. But the weight of the block is 7 newtons. Well, of course, the block's going to sink. The only way it's not going to sink is if the... Well, we'll come to that, actually. I don't want to talk about that right now. So if the weight of the block is bigger, so if this number here is bigger than the number pushing back up on it, so the up thrust, then the block will sink. That's logic. Scenario number 2. Again, move this up a little bit. Let's say the weight of the block equals the weight of the displaced water. Then what do you think will happen if instead of 7 newtons, this was 4 newtons? What then? So 4 newtons up, 4 newtons down. What is the resultant force on that? The resultant force, if there's 4 up and 4 down, will be 0 newtons. Okay, there will be a resultant force of 0. So what will happen is the block will float. Okay. Finally, I want to talk about what if the weight of the block is less than the weight of the displaced water, which you can't even see me writing anyway. Can you? Let me fold this a bit so we can fit more in. So the weight of the block is less than the weight of the displaced water. Well, hold on a second. So our scenario now, here's my block. Let's say weight of this amount of water is 8 newtons, but the block is 4 newtons. That's impossible. Okay, because the resultant force in this scenario would be 4 newtons upwards, and if you've got a resultant force, something is going to happen to that block. And in this case, the water is going to fling the block out of the water. Have you ever seen that happen? I've never seen that happen, because it doesn't happen. It's impossible for the upthrust to be greater than the weight of the block, because, you know, if it was 4 newtons, let's ignore that. If it was 4 newtons downwards, actually I shouldn't have ignored that. And that was, but the actual weight of